Hello. In the last episode, we talked about the parallel circuits, and before that, we talked about series circuits, and we talked about the Christmas lights example and why, in order to illustrate the different rules involved with both parallel and series circuits. For example, with a series circuit, if I hook all the light bulbs up in series, if the filament burns out in one of them, there's no path for electricity to flow, because remember, you have to have a complete path for electricity flow. So not only does that one light bulb burn out where the filament burns out, but it also will stop current throughout the whole circuit, so none of the lights will light up. We talked about how you could remedy that situation by hooking the lights up in parallel, and that provides a better situation because now in a parallel circuit you have multiple paths for current to flow. So just because one of the filaments or one of the lights shorts out doesn't mean that you necessarily lose the power to the other lights, and in fact you wouldn't. So we talked about our poor Waldo with his 2,000 light string of lights trying to outdo, I guess, Chevy Chase, lighting up his house, using up all the power for the neighborhood for his Christmas display. And you've seen this happen. I've seen folks out there where they're like struggling to pull the lights out one by one in a series circuit. It's very frustrating, although somewhat comical. So we talked about with a parallel circuit that doesn't happen. You have the multiple pathways for current to flow, so just the one light will burn out, but the other lights will light up. Now occasionally you may have a situation where you have both a circuit which has both a series component and a parallel component. And today I want to talk about that and how you would solve for the different values in such a circuit. So let's just draw up an example here. Okay, so this is a drawing. Hopefully you can see it. I know this has been a problem on all of these. And I have my 3 light bulbs here in parallel, although I've drawn them a little bit differently. But the point is that if one of them burns out, you still have a pathway for current to flow through the other light bulb so that you don't lose power to all of them. But let's say that I wanted to put a fuse in series with my lights so that if for some reason the current got too high, this fuse would burn out, and I want it to be in series because I want it to cut the current flow completely to the rest of the circuit. So that might be one instance where you would have a situation where you have both a series component and a parallel component in the same circuit. Now to solve for this, it's going to be very similar to how I solved for well, actually, you're just going to apply the rules for both series. You're going to apply the rules for series circuits to the series portion and apply the rules for parallel circuits to the parallel portion to solve for this really seemingly, but it's actually not too complicated circuit. Okay, so and just a reminder here, what are the values that we're going to be working with? What are the quantities that we want to know about? We want to know about the voltage. What's the electrical pressure that's pushing electrons through this circuit? Remember, the voltage is not the movement of the electrons, it's the pressure or force that causes the electrons to move from the negative terminal to the positive terminal. And it's measured in volts and represented by the letter E in most electrical formulas. We're also going to be concerned with I, which stands for intensity, and that's the intensity of the current flow, and that actually is a measure of the electron movement through the circuit, the actual flow of electricity. And then that is measured in amps and represented by the letter I in formulas. And then finally, we talked about that if you didn't have any resistance in a given circuit, all the current would try to flow as fast as it could from the negative to the positive terminal, and it would heat the wire up, and essentially what you'd have is a short circuit. We don't want that, so we want a certain amount of resistance. Resistance is represented by the letter R, and it's measured in ohms. Now let's take a look at this particular circuit. So what are our rules for series and parallel circuits? And I probably will have to break this up into 2 videos because it just gets I can't go over about 15 minutes or so, or I can't upload these. Well, in a series circuit, I want to remember a couple of things. With the series circuit, we want to remember, and let me see if I can find that to put that back up here for you. So here would be an example of a series circuit where there's only one pathway for the current to flow, and remember that these different resistances here, which in this case represented light bulbs, each of which had 50 ohms of resistance that it offered to the flow of current in the circuit, we add these resistances up for the total. And remember also that since there's only one pathway for current to flow, that the total current is going to be the same as it is at each one of these points throughout the circuit. So the current flow through R1, the I at R1 is going to be the same as it would be at R2 and R3, etc. And then also remember that there are voltage drops, so there's a certain amount of pressure required at each point to push the set amount of a current through the circuit. So there will be a voltage drop here at R1, a voltage drop here at R2, and a voltage drop at R3. We should be able to add all of these voltage drops up, and that would equal the source voltage, in this case, of 120 volts. Now, let's quickly review the rules for series circuits, or sorry, parallel circuits. So here I have a parallel circuit, and in this case, everything is kind of reversed. So here, the current is not going to be the same at all points throughout the circuit because it has different pathways to flow through, different paths to flow through. So it actually splits, and it's divided among the various branches of the parallel circuit. So what is going to be the same, though, is the voltage. So instead of having voltage drops, we actually have a situation where each resistance is hooked up directly to both the negative and positive terminal of the voltage source. So there's going to be 120 volts of pressure at R1, 120 volts of pressure at R2, and 120 volts of electrical pressure at R3. So we're going to have to add up the currents through each branch to get the total current. And then also, although this is counterintuitive, even though we have 50 ohms of resistance in each of the branches, and it might seem like you would add these up to get a total resistance of 150, remember that each one of these resistors also is set up in a separate path for the electricity to flow, which means that the total resistance will be less than the value of an individual resistor through one of these branches, and so it should be less. And we talked about how you use the reciprocal of the reciprocal formula to figure out what that total resistance is. But here again, it will be less than the value of any one of these individual resistors. Okay, now that we have reviewed our rules for series and parallel circuits, let's get back to this situation. Now, as I said, in the real world, this first resistor that I have shown here in my series parallel circuit might actually be a fuse, but here I'm going to just use a 100 ohm resistor, and then we're going to keep our lights, our same 3 light bulbs that we've had in the other circuit. So R2 represents the first light bulb, and it offers 50 ohms of resistance. R3 represents the second light bulb, and it also offers 50 ohms of resistance. And R4 represents the third light bulb, and it also offers 50 ohms of resistance. Now, to solve a series parallel circuit, I'm going to apply the series rules to the series portion of the circuit and the parallel circuit rules to the parallel portion of the circuit, and I may have to use equivalent resistors to try to simplify the circuit to solve for the total resistance. Now, what values do we know in this circuit? We know almost everything, but we do not know the current flow, the total current flow through the circuit. We want to find that out. We also want to find out what the total resistance is throughout this circuit. So we're going to have to do a little bit of math here, although it's not too painful. What do we know? We know the source voltage or electrical pressure. We have a difference of potential of 120 volts. We have these different resistance values, but we don't have a total current and we don't have a total resistance value. So what we're going to do first is try to simplify this by first solving for the parallel portion of the circuit by applying our rules for parallel circuits, and then we're actually, once we find out what the total resistance is here, we're going to pull these out in the imaginary sort of way and replace them with an equivalent resistor that's going to be in series with this 100 ohm resistor that I have right here. So what do we need to do? Well, remember, our formula for parallel resistance is the reciprocal of the reciprocal of the various branch resistances, and I just add those together. So we're going to represent this by RA because it's not the total, it's just the total for the parallel portion of the circuit. So RA is going to be equal to 1 over R2, which is the first light bulb, plus 1 over R3, which is the value in ohms of the second light bulb, and then plus 1 over R4, which represents the third light bulb, and it also is 50 ohms. When we do the math on this, it gives us a total value of 16.67 ohms. Another way that I could find this, and this will only apply if all of the resistors in each branch is equal. This would not work if these, let's say that R4, if this was, I don't know, 240, then I couldn't do it this way. But since all of these resistances offered by the 3 light bulbs are the same, they're each 50 ohms. Another more simple way that I can solve for the total resistance here is just to take the value of a single resistor, 50, and then divide it by the number of them for the 3 branches, or the number of 50 ohm resistors rather, and I wind up with the same number of RA equals 16.67 ohms. So that's my total. Now that I have the total resistance through the parallel portion of the circuit, I can redraw it and simplify it to find the total resistance flowing through the circuit overall. So I'm going to redraw my circuit. I'm going to take out those 3 light bulbs, and I'm simply going to replace them with what's called an equivalent resistance. So we're going to pretend like this is an equivalent resistor that has the same resistance value as the total resistance in the 3 branches that were in parallel. And we're going to have that resistor set at 16.67 ohms, which represents that total that I just mentioned. Now I have a simple series circuit, and all I have to do to find the total resistance for this whole circuit is add those 2 resistors in series. Because remember, with a series circuit, all I have to do is just add the resistances up, and I wind up with the total. So let's do that right now. RT is going to be R1 plus RA, and then we plug in our numbers, and we have 100 ohms plus 16.67, and we wind up with a value of 116.67 ohms. I now have everything that I need to solve for the total current that flows through the circuit, and I can do that, find that out by just using Ohm's law. And here I have Ohm's law, the formula listed for you. It's going to be IT measured in amps. We're trying to find the total current measured in amps would equal the total voltage divided by the total resistance. Well, we know our source voltage coming out of the wall is 120 volts. So I then divide that by the total resistance, which we now find to be 116, and I wind up with a total current down here, of 1.028 amps. So this represents the total current flowing through my circuit. Okay, now in the second episode, so this is actually a 2-part because if I try to do this in one video, it'd be too long. I'm going to show you how to go back through and do some checks on this to check our math and make sure that it all adds up. All of these different values add up. But the key thing here, just a quick summary. If I have a series parallel circuit where I've got a part of the circuit's in series and a part of the circuit has parallel components, all I need to do is apply my series rules to the series portion of the circuit and my parallel circuit rules to the parallel portion of the circuit. And here again, the real world example that we're using is where you have a fuse in series because we want it to cut off power to the rest of the circuit. We don't want any power flowing if the current gets too high and it burns up that fuse. So that part needs to be in series. And then we have the light bulbs, which are in parallel because we don't want the current flow to be cut off to the other light bulbs should one of the filaments burn out and create an air gap, which is essentially going to be an open circuit to that light bulb. or through that light bulb. Okay, so that's a summary. Now in part 2 of this, we will do some math checks to make sure that we did our math correctly and found the correct values of resistance, current, and voltage in our analysis of the series parallel circuit. Thanks for listening.